Hello again, my dear students, and welcome in a new chapter with our module. Today, we are going to consider a macroscopic view toward the sensor, targeting to what's called an energy management in a sensor. As you can see from our previous lecture, energy is considered as a key parameter whenever you are considering a system, either from the point of from the point of the view of the supply, whenever you are harvesting energy. So you are trying to capture or to harvest as maximum energy as you can, or from a consumer point of view, where you are targeting to optimize your energy consumption toward minimum energy consumption. What we are going to do today is to see how we can calculate the power and the energy for a sensor, and then how we can act toward optimizing this energy to be consumed in a sensor. Okay, so let me first start sharing my presentation slides, and let's start our journey with this chapter. Okay, as you can see from the title of this chapter, we are going to consider what we can call, so I think I have a problem with the share, so I'm just going to reshare again. So I think now I'm right. Yes, okay. As you can see from the title of this chapter, our concern is, or our example or case study today will be considered toward a self-powered sensor. A self-powered sensor, maybe we already introduced this before in the previous lectures, that a self-powered sensor is this smart unit considering not only the sensing part of the sensor, but also the processing part, the communication part, and the energy part. So it's a sensor with an interfacing circuit in the back stage and some communication link. And in the other hand, you have an energy supplier or a battery with an energy management system to consider the balance between the consumed power and the supplied power. So what we are going to see now is how we can consider a power consumed in a certain CMOS sensor and how we can optimize this power or energy toward an optimum smart sensor. So in this case, we will consider an example to reflect our ideas on. And our example will be a temperature sensor. And as I just mentioned, we are not considering a conventional temperature sensor, but we are considering some sort of a CMOS transistor sensor. And this is toward what we can call a sensor on a chip, so that we can have all the sensor component of our smart sensor to be integrated in a chip. So our temperature sensor looks like that. So before considering the power consumed in this sensor, let's first start discussing how this sensor will be used to measure temperature. And in order to do so, let me return to my whiteboard. If you permit me to do so, I will turn to my whiteboard and close sharing screen. So let's do it. How this circuit will measure temperature. Okay, let's see how this circuit will work. So our circuit consists of we have here two current sources, and then we have two transistors connected in this direction. And here we have the negative terminal. We have a PNP transistors and this is I, and this is P times I. And of course, here we have VCC, and here we have negative VCC. We will call this VBE1, and we will call this VBE2. Okay. So how this circuit will be used to measure temperature? As you know from your previous courses, whenever you connect a PNP or a NPN transistor with this configuration, I mean, you just shortcut that base collector junction. That means you turn your device to work as a die. You have only one junction now acting, which is the VBE, or here it's called EP junction because it's PNP. So the P is the emitter and the N is the base. So in this case, you can write, or you know that the current flowing in a die is equals to I equals IS, or the saturation current, e to the power V over VT minus 1. This is the current flowing in a die. And as you know, here the voltage applied is VPE. This is the voltage applied to the diode. So I can write I equal IS, or the saturation current, e to the power VBE over VT minus 1, as you can see. Now, for a relatively forward bias, I mean, whenever this VPE is greater than V, or greater than or equal V in, this exponential would be much greater than 1. So we can write I equals IS e to the power EVPE over VT. And by ln, or by multiplying by ln both sides, you can get that. We will use this later on. So what we say is I equals IS e to the power VPE over VT. So e to the power VPE over VT equals I over IS, multiplying by ln both sides. So VPE over VT equals ln I over IS, or finally, the final equation is VPE equal VT ln I over IS. So you can just directly use this equation to link between VPE, or the voltage applied on the transistor, or between condition of the die, and the current flowing in the die. So I'm sorry. So using this equation for these two transistors. So here the voltage applied is VPE 1. And here the current flowing is I. While here the voltage applied is VPE 2. And the current flowing is P times I. So we can write two equations, one for the first transistor and two for the second transistor. Let's see. Okay, so VPE 1 equals KT over Q, or VT, both the same, of course, ln I over IS. And for transistor number 2, we can write VPE 2 equals KT over Q ln P times I over IS. So this is an equation for transistor number 1, and this is an equation for transistor number 2. Perfectly. So if we define what we can call, if we define what we can call delta VPE as VPE2 minus VPE1. So this is the difference between these two VPs. So Using this, delta VPE will be equals to VPE2 minus VPE1, which is KT over Q ln PI over IS minus KT over Q ln I over IS. Taking KT over Q as a common factor and using the fact that subtraction of limb gives division or fraction. So you will get I cancelled with I, IS cancelled with IS, you will get ln P, and this is delta VP. So let's examine this equation. Delta VPE equals KT over Q ln P. What is P? P is a design parameter we defined in the beginning of the circuit as the fraction or the fractional ratio between this current source and this current source. So it's a design parameter, which is obviously it's a constant. K, which is a Boltzmann constant, Q, which is a unit charge. So simply, as you can see here, delta VPE is directly proportional with temperature, where the constant of this proportionality can be defined as K over Q ln B. And this will be turned to the sensitivity of your sensor. So with each increase or decrease degree Celsius of this temperature, the voltage will change by this factor, which is K over Q ln B, with the unit voltage per degree Celsius. So this is the sensitivity of your sensor or your temperature sensor, CMOS temperature sensor. Okay, so this is the design equation, how we can consider this VPE or delta VPE in order to measure temperature. But before proceeding to the next step, we have to highlight some points here. First point is, principally, VPE1 and VPE2 also directly proportional to temperature. So maybe a question is asked now, why we consider delta VPE, not VPE1 or VPE2? And the answer here is very easy. Yes, VPE1 and VPE2 are directly proportional to temperature. However, they are not the only variable in the equation, because with the changing temperature, the current source may change and the saturation current may change as well. So changing temperature in this equation will not only reflected by temperature, but it will reflect by T, I, and IS, so that you don't have this direct relationship between VP and temperature. A second question, or not a question, the second important point to be mentioned here, that following this reversion, we have making a very important assumption that we assume that IS1 and IS2 are equal. Or in other words, we are assuming now that the two transistors are identical, which is not commonly the case, because sometimes you have some mismatching, let me say, between these couple transistors. So this can attribute to the equation somehow, and we will examine this in the next step as well. A third and an important point here, whenever you do any measurements, you have to have what we can call a calibration or a reference. I mean, you have to have a signal that gives you a reference concerning the voltage you are measuring. So we can say that this circuit, this simple circuit we see, this circuit, this one, we can say that this circuit is a good circuit to measure temperature. However, it's not complete circuit for a sensor because, or due to the absence of a reference signal. So now what we are going to consider is how to have this absolute signal or reference signal, and how to consider the case if these two transistors are not identical. So let's see what we will do to tackle or to consider these 2 points. Back to slides. Okay, so this is the updated signal. As you can see, my dear students, first of all, we have still the same sensor concept here. So this, what is inside the box is identically the same as what we already see in the previous slides, but with a minor change. If you have a good concentration, you can pick up this change that yes, I got it. Yeah, that now we have this factor. Now we consider this R factor to represent a mismatching factor between Q1 and Q2. So that now if this area is AE or the emitter area is AE, here the area is R times AE to consider the mismatching. So this is the first point. Now, for other points as well, this is the same circuit, but now we have a third transistor or a third branch with a different current. It's called I2. Driving this, we call this VPE. And then this is typically the same value we just measure, which is VPE2 minus VPE1, but only we have added a multiplied differential factor, which is alpha. So the output of this VBtat, or we call it V absolute, VBtat, is alpha delta VPE. And then you get this alpha delta VPE and you add to this what's called a the voltage coming from this VPE1, and you call this as a P reference. So let's see how this circuit is working. So principally, the voltage VPtat is typically the same as the voltage we just calculated, which is delta VPE, but with only adding this multiplication factor. So just going to the to our circuit for a while, we can say that VPtat is equals to alpha delta VPE, or we can say that VPtat equals to alpha times KT over Q ln P times R. Now take care, my dear students. I add this R factor, which appears to be a mismatching factor. How this R is added? It's very simple. Let's turn to this equation. If you remember this equation, here we consider IS and IS are the same. What simply I can do is that if I consider that if it's this current, if the current for transistor number 2 is called IS, then the current of transistor number 1 is called R times RS. So that's, I now include that effect in the current, so the current number is R times RS. If you go with the same revision till this point, when you do subtraction, now this is R times RS, so you will find that it will be P times R. So this is the factor you are measuring. By the way, concerning the sensitivity, maybe I forgot to mention that, of course, K and Q are constant. So your sensitivity now can be adjusted with the term P, which is a design parameter, as I just mentioned. And as you can see, you can also use P to compensate R. So whenever you have any mismatching factor, you can include P to compensate this R factor. Okay. So this is the PTAT, which is alpha KT over Q ln P times R. This is simply the PTAT value. Let's now go to, again, let's okay, I'm sorry for this. Let's now return back to our slides and let's see now what is this voltage. As you can see, this branch is identical to these two branches, of course, with different values, because here we have I2, but we can still use the VPE equation. So we can write a VPE equation here. Let's now return here. So we can write that VPE equals KT over Q ln I2 over IS. Of course, here I consider I2, and let's call this IS2 to consider that this is the saturation current for transistor number 2 or whatever. So this is an equation that represents the VPE. Okay, so now we can calculate V reference. If you can see their slides now, you know that V reference equal VP tot plus VPE, which is equals to KT over Q ln P times R plus KT over Q ln I over IS. Okay, now let's describe or let's concentrate deeply on what is the meaning of the word reference. A reference value or an absolute value, this value should be independent on the parameter to be measured. So whatever the temperature is, this reference should be kept constant all the time. Or in other words, in order to have a reference in terms of a temperature sensor, it should be that partial V reference by partial T should be equal to 0. So that we can call this a reference. So let's see. Is it possible? I'm sorry, I just forgot here that there is an alpha factor here. So I'm sorry. So is it possible to manage that this partial R V reference by partial T is equal to 0? Is it considerable? Let's see. So as I just mentioned, V reference equals alpha delta VPE plus VP, which is alpha KT over Q ln PR plus VPE. Let's try to differentiate this equation. So in the first term, we know that all other parameters are constant. So alpha is an amplification constant, which is a design parameter. K and Q are Boltzmann constants and temperature. B is a design parameter, and R is a mismatching area factor. So differentiating this term with E, simply given alpha K over Q ln PR. What about this term? Okay, this is actually an uncontrolled term. This depends on the circuit. So if you can just see here, so this is simply a voltage edge coming from this branch, which is uncontrollable because simply this current source may be affected, or most likely it will be affected with temperature. This transistor, as well as the saturation current in the transistor, will be affected by temperature and so on. So this is an uncontrollable term with respect to temperature. And in other words, it can be measured, but it cannot be controlled. I can just change the temperature and measure how the VPE will change, but I cannot control how this will happen. I will just observe that. So I will add a term here calling that this is simply partial VPE by partial T. And now our target is, as you see here, sorry. Our target here is to make this parameter temperature independent. So we need to make this differentiation is equal to 0. So the back of this equation. So we need this equation to be equal to 0. Or in other words, we need alpha KT over, K over Q ln PR to be equals minus partial VPE by partial T. If this condition happens, then that means that the differentiation will be equal to 0, and that means that your reference voltage is now temperature independent. Is it possible to make or to sustain this condition? Simply yes. How? Because we have this new parameter alpha, which is a controllable design parameter. So if you put alpha to be equals to Q over K ln PR times minus partial VPE by partial T, that will make your reference voltage an independent voltage with respect to temperature. And it's a reference voltage. So that's why we introduced this new parameter called alpha in the equation. In the previous version of a sensor, we just subtract delta VPE, which is VPE2 minus VPE1, and that's all. But now, by adding this alpha parameter, which creates a new axis of freedom for us to design the equation in this manner so that we can get a reference voltage, which is a temperature independent. So back to the slide. So by inserting an alpha equal to this factor, minus partial VPE by partial T, Q, K, ln PR, you can guarantee that your reference voltage now is a temperature independent voltage. You can see this using graph, and I think this is a very, very useful graph. As you can see, this is a VPE versus T. So by making the experiment, I just mentioned that this is not a control the parameters. This is just a measured parameter. So I go to the lab and I measure this variation of the VPE with temperature. Now I have delta VPE. What I can do is that I can multiply this delta VPE by a factor alpha so that the equivalent reference voltage is temperature independent. And this is a very important concept in electronics. So that in order to create a voltage which is temperature independent, what you simply do is you combine two voltage. Each of them is a temperature dependent with an alternating or a reverse polarity. So your temperature dependent of the VPE against temperature takes this negative trend. So you have now a compensating positive trend so that you get this reference voltage as a temperature independent value. And we call this a reference voltage, or maybe the most familiar and common name in literature is to call this or to consider this as a band gap voltage. Actually, the word band gap comes from the number 1.2, because as you know from your semiconductor background, that silicon has an energy band gap of 1.2. That's why it is usually called a band gap voltage. And you can now understand that a band gap voltage is a voltage that is a temperature independent voltage coming from summing two different voltage dependent or temperature dependent voltages with a compensating effect so that the resultant is a temperature independent. And this is a very important concept in electronics. So this is simply how these sensors work as. However, so far, we didn't consider the main point of the lecture as how we can measure the power consumed in this sensor or in this CMOS sensor. So back to this simple circuit, and let's start now considering this simple circuit in order to calculate the power consumed in this circuit. So simply, you can say that the power consumed in this circuit is the power consumed in the power supplies in addition to the power consumed in the transistors. So let me write an equation here. So let's say that the power dissipated, the total power dissipated in the sensor is equals to the power dissipated in the first power supply, the first current source, which is VCC times I, plus the power dissipated in the second current source, which is VCC times I times P, plus the power dissipated in the first transistor, Q1, and the power dissipated in the second transistor. So let's see what is how much the power is dissipated in the first and the second transistors. Let's see here. As you can see, my dear students, or from your previous knowledge about transistors, the power dissipated in the BGT is simply equals to the power or the current flowing in the BGT multiplied by the VCE. And as you know, due to this short circuit, VPE and VCE is equal. So simply, the power dissipated in this Q1 is the current flowing in this Q1, which is I, multiplied by VPE1. And here it's PI multiplied by VPE2. So we can write an equation like that. So that's power dissipated equals to VCC times I times P plus 1 plus VPE1 times I plus VPE2 times I times P, because the current flowing in number 2 is IP. As you can see, my dear students, this result was a very important factor, and that's why I'm considering this equation. Some paper or some slides ago, we have mentioned that the sensitivity of our sensor is K over Q ln PR. And here we have found that P is considered as the main design parameter in order to control or tune your sensitivity. But as you can see also here, that the power dissipated in your transistor or your sensor is also factored in a P. So this P is a very critical design parameter in such a sensor. In one hand, it controls the sensitivity of a sensor. And in the other hand, it also determines the overall power dissipation in a sensor. I think it will be very interesting when you go to the problem sets in a tutorial and solve this with numbers so that you can express the importance of P in calculating both the temperature, the sensitivity of the temperature sensor and the power dissipated by the temperature sensor. So here you can find an equation for the power factor in P. Okay. I'm sorry. Okay, perfect. But let's come to another question. Does we need to measure temperature 24/7 all the time? Actually, most likely, not only for temperature, but for any parameter, the answer is no. Usually, you are working toward measuring the parameter or the sensing physical parameter or biomedical or whatever. You are intending to do this process in a periodic way. So, for example, I need to measure the temperature of the water, for example, if this is an underwater sensor. So I will need to measure the temperature of the water once every 1 minute or once every 5 minutes or whatever. This is actually a very important parameter in the energy management. This is simply because you don't need to turn on your transistor or your CMOS transistor sensor all the time. You have to have two modes of operation. What we call an active mode, during which you are doing your sensing process, and the other is what we can call a sleep mode, where your sensor is turned off or ideally turned off in order to minimize the energy consumption. So, for example, if we, sorry, share screen. If we consider this sensor, for example, and if we add something like that here, so this is basically a very simple MOSFET with a gate signal acting as a switch. So that in this gate signal, I'm going to consider something like that. As you know from your background related to MOSFETs, that simply means that your sensor will only turn it on during this high signal, so that you have a sensing process here. Otherwise, during the low signal of a gate, your sensor or your switch is turned off. It's an open circuit and it's no longer working. So that's automatically attributed to the energy consumed. So simply, the energy consumed here is directly proportional to the area under the curve, where we consider this as what we call the sensing time, which can be something in microseconds or milliseconds. So in every 5 minutes, you will only open or turn on your transistor for just milliseconds to sense the physical parameter to be sensed. Otherwise, your sensor is turned off and your energy consumption is minimal. Of course, ideally speaking, whenever your sensor is turned off, that means that this is ideally an open circuit, which means that basically there is no power dissipation, because in an open circuit, current is equal to 0, so there is no power dissipation. However, with a deep understanding for MOSFETs in the CMOS technology, you can know that, practically speaking, in the off mode or in the sub-threshold mode, your current dissipated in a MOSFET is not ideally 0. However, we have what's called an off current, which represent some very small current to be consumed even if the signal reaching the gate of a transistor is below the threshold, or what we call a sub-threshold region. That means that, physically speaking, in this region, you still have some power dissipation. Of course, you should act towards performing or choosing MOSFETs with maximum on-off current ratio, or in other words, with minimum of current, so that you can minimize the power dissipated in the sleep mode. But practically speaking, you have to consider that there is still some power dissipated in the sleep mode. Of course, it's much lower than the power dissipated in the active mode, but it should be considered in terms of region, as you have a big region or a long interval of sleep mode. So even with a low power, this accumulates on energy. So this is basically how we can manage a circuit to optimize the energy, of course, in a very basic and very brief manner in terms of energy management. You can repeat the same process here with considering the third branch, which still have an additional current source and an additional transistor. So you can repeat the same process here, and you also can calculate the overall power dissipated in this equation. So this is simply how you can consider a CMOS transistor, or sorry, a CMOS sensor, and how you can calculate the energy consumed in this CMOS sensor. That's all from my side, my dear students. Thank you very much for your concentration, and see you in the next lecture, inshallah. Thank you very much.